meters, 0 seconds, or 0 position, 0 seconds. At t3, it's back to where it started. It has the same position. So again, objects rolling away from the initial position stops, and then the object's rolling back to where it started. We're going to actually calculate the slope here, and I promise eventually. So a positive slope, it's moving away. 0 slope, not moving. Negative slope, moving back to where it started. And we'll talk about how to find average velocity from a graph. Now, calculating average velocity is change in position over change in time. Distance is the velocity times the time, and then time is the distance divided by the velocity. So before we were looking at questions, they didn't really say which formula to use, but if it said, how far has an object traveled, you say, okay, how far? I'm going to use the distance formula because it's asking me to find how far. Or if it said how long, I'm going to try to find time. And again, these are all in the back of your data booklet, these 3 formulas. We've seen them before. We're just looking at them in a new light now. All right, let's do some examples. We have 4 lines here, A, B, C, and D, different colors. And we are asked to figure out which one has a slope of 1, which one has a slope of 2, which one has a slope of -1, and which one has a slope of 0. So let's maybe start with the easy one. Which line has a slope of 0? That's probably not too difficult. Just throw the letter into chat. 0 slope. We have a C. Have any other votes for C? Another vote for C? Okay, that was the easy one. C has 0 slope. Now, this is where it might get a bit tricky, but I think you guys can handle it. The other ones are asking for a slope of 1, 2, and -1. But I don't have any numbers to deal with. I don't know what my distance is. I don't know what my time is. So how can I actually find a slope? Well, I'm just comparing them, right? I don't need a specific value, but I can say, okay, if C is this, then maybe A compared to it is this. -1 is D. Okay, a negative slope is down to the right, and D is definitely going down to the right. So that would be negative. I would agree with you there, Taylor. Anybody disagree with that? Are we happy with the negative slope there? Now, the next 2 slopes are 1 and 2. Yes, Abby, distance time graphs and position time graphs are generally the same. Yes. Yes, just for the purposes of what we're doing, yes, they're the same thing. I don't know what's 1 and I don't know what's 2, but I can compare A and B to one another. And I can say, okay, A is a little bit steeper, B is less steep. Wouldn't it be B because right under the 0 for -1? Remember, Ava, we're talking about slope here. So it can be, if we even look at A here, you can see it goes down a little bit into the negative in this quadrant here. It's still, the slope is going up and to the right. So if we were talking about something like position, you might be right. But in this case, we're talking about slope. So the slope of the line is the rise over the run. So if I look at A, it looks like it's about twice as steep as B. A is going to be 2, B is going to be 1. Just relative to one another. Second example here says, what would it mean when a distance versus time graph shows a negative velocity? I'm actually going to jump over here and scroll down. There we go. So I can write negative velocity. Distance versus time graph. Let's maybe just draw a graph quickly. It doesn't have to be pretty. Of course, you guys always use a ruler when you draw your graphs, but I am not going to. So there's the distance time graph. What would it mean if we had a negative velocity? Now, I kind of just glossed over a point, but it was really super important. And I said the slope of a position time graph is your velocity. So how would I indicate a negative velocity on this graph? What would that look like? A negative velocity would indicate a negative slope. So if I wanted to draw a graph a position time graph with a negative velocity, I would have to have a negative slope. So I could draw a line like that. There we go, a little line segment. That definitely has a negative slope. It's going down and to the right. So that means it would be a negative velocity. Okay, let's look at a few more examples. I really like this example. I think it's a good one. Following data were graphed for a 100-meter race between Bob and Ed. Everybody's favorite runners, Bob and Ed. Again, if you were to describe to somebody who wasn't at this race, again, your mom, dad, little sister, brother, what was going on? What's happening at the race? You can tell a ton of information from this graph. So it's a 100-meter race. I check and I see that I have a position time graph or a distance time graph. Same deal. A distance versus a time. Okay. What's going on here? Bob's the red line, Ed's the blue line. I need to describe what's going on to somebody who's never seen this race or doesn't really know what a position time graph is discussing. So, first of all, maybe let's go with who won the race. Who won, Bob or Ed? It was a 100-meter race. Here's 100 meters up at the top. Who won that race? Bob or Ed? Any ideas? Ed catches up to Bob. Ed did catch up. Ed won the race. Who thinks Bob won the race? We have one vote for Ed, and Ed's catching up to Bob. We'll get to what that means in a second here, Taylor, because that's super important. I would look at my graph and I would say, okay, I'm interested in 100 meters. It's a 100-meter race. So I'm going to go to 100 meters. I'm going to go across on this line, and I'm going to see who got to 100 meters first. Now, it kind of looks like both lines are at the same point at 100 meters. And if somebody asked, I would say, okay, that 100 meters took them 10 seconds. If I didn't have this red line, if I took out Bob's line, you would say it took Ed 10 seconds to get to 100 meters. Okay, now I'm going to look at Ed's line, Bob's line. I'm going to get rid of Ed's line here. And I would say, okay, it took 10 seconds for Bob to get to 100 meters. So if I looked at each of the lines individually, they both end up at 100 meters at 10 seconds. It's a tie. Both runners get to the finish line at the same point. But Taylor said something really important earlier. She said Ed catches up to Bob. What does that mean? How do we have different slopes? We have two runners running a 100-meter race. How could somebody catch up to the other guy if they're both crossing the finish line at the same time? There's something really important in your statement, Taylor, Ed catches up to Bob, that we need to kind of discuss a little bit further. One of the slopes is clearly steeper than the other. Ed, his slope is steeper than Bob's slope, meaning Ed was running faster because the slope of the line is the velocity. So how can two people finish a race at the same time and they could be running at different speeds? Because their slopes are different, that means they're running at different velocities. What important information have we not discussed yet in terms of this race? What do we think? Bob's start. You want to elaborate a little bit further on that, Taylor? Because you're completely right. What was special about Bob's start? Taylor's now a little bit closer. You guys are both right. You're on the right track. Bob didn't start at 0. Bob, what are you doing? All right, so this is 10 meters here. This is 20 meters. So at 0 seconds, Bob was right here. Bob got a 20-meter head start. Bob. Ed started at 0 meters at 0 seconds, but Bob started at 20 meters at 0 seconds. So Bob got a 20-meter head start. Maybe Bob was old or something and he needed a head start. Or maybe he cheated and started 20 meters down the race course. Bob he only ran 80 meters. He started at 20 and he finished at 100. That's only 80 meters in there. So he didn't actually run a 100-meter race. That's why his slope of Ed is a lot steeper, because Ed ran 100 meters. He had to run faster because Bob got that head start. I love this question. It's a great question. It really makes students pay attention to the axes, what they mean. And if you're kind of understanding that Bob got this head start, you're understanding what the points on the graph mean, which is a good thing. All right, let's look at a couple more examples here. And I don't want that. I want that. All right, so let's think about this. Similar scenario, but maybe a little bit different. A blue car was driving at 60 kilometers per hour. A red car was driving at 100 kilometers per hour past that blue car. What would this look like on a distance versus time graph? And how would we know when a pass occurred? What special thing would happen on a graph when the blue car got passed by the red car? What would that look like? Would it be an intersection of one of the axes? Would a line cross something? Maybe if you have a piece of paper in front of you, just draw a little quick graph and see if you can figure out what a distance versus time graph for something like this would look like. So you have a blue car driving at 60, gets passed by a red car at 100. What special thing will happen when the cars passed each other? What would that look like on a graph? How could I indicate that on a graph? I actually have some video footage of the car race here. I have a blue car and then a red car. Zoom. All right, so my blue car traveling at 60 kilometers per hour. The red car is traveling at 100 kilometers per hour. Now, it's not really important that the blue car starts at 20 meters, and it's not important that the red car starts sometime after, but what is kind of important is the red car enters the race about 4 seconds after the blue car. And when the cars intersect right here, which is the same thing as right there, at 60 meters, they both are at the same spot, which also happens to be 7 seconds. So 7 seconds after the race began, the cars are at the same spot. But because the red car is going faster, it actually passes the blue car. So, you couldn't figure out how they figured out how far it should start ahead. I guess it's not really important. As long as you're just trying to figure out what's happening, you're always going to have two lines that cross. The important thing here is the slopes of the lines. The blue car had a speed of 60, so it should have a slope of 60. The red car had a speed of 100, so it should have a slope of 100. So if you have your blue line and then your red line should have a steeper slope, and it doesn't really matter how long of a head start you gave it. If you drew that red line here, it would just pass it a little bit sooner. If you started your red line at 8 seconds after, you'd have the same slope, but the lines would just cross a little further along. So That's what's happening in this little example. Okay, let's see if you guys have put all these pieces together. Is anyone brave enough to describe what's happening in this graph? And if it helps, you might consider drawing a graph. I don't like this graph. It's in threes, and that bothers me a lot, but I'll get over it. 3, 6, 9, 12, 15, -3, -6, -9, -12. Okay, just draw a little sketch. Doesn't need to be pretty. I'm going to put my tree at 0 meters, and we're going to describe the motion of the object. Now, Taylor, one thing that is really important is that when you say it goes up, you're indicating a direction. Up is the direction. Now, just because the line is increasing in slope, does not mean the object's going up. And I think Anna said something like this before. It's super duper important that every time you see a slope that's increasing, you don't assume the object's rising in the air. That's not what this means on the graph. So let's look at the graph and figure out what's going on here. All right, so I have some 0 position. It's completely arbitrary. I've drawn a tree there. There we go. I've picked 0 position. At 0 seconds, I'm talking about this red portion of the line here. All right, at 0 seconds, where is my object? Anna, you're right. It has a positive slope, so it's going to the right. This says displacement. I don't have any indication of what displacement means, but I'm going to assume everything to the right is positive. And that's an assumption that I'm willing to make. So 0 seconds is this line here. Where does my object start at 0 seconds? Does it start at 0? Does it start at the tree? Or is something else happening here? This is kind of like Bob and Ed. One of them got a head start. Didn't start at 0 meters at 0 time. If I look at my graph, this is -3 right here. So at 0 seconds, my object is -3 meters. So here's my little ball, and this is 0 seconds. It's not starting 0 meters at 0 seconds. It's starting at -3 meters at 0 seconds. Okay, 3 seconds later, roughly, it's actually a little bit more than that, it looks like about 5 seconds, it's at 0 meters. So I'm going to draw the ball right here. This is at about 5 seconds. It's at 0 meters. All right, let's keep going. At 6 seconds, let's find a nice spot here. At 12 seconds, it's at 6 meters. There we go. That's 12 seconds. So it kind of looks like my ball is rolling to the right. And Anna, you were right when you said, it's going to the right, isn't it? Perfect. All right, now my object is at this little horizontal line here. What does that mean? From 12 seconds to, this is 15 seconds in here, what is my object doing from 12 seconds to 15 seconds? It's not moving. Perfect. There's 15 seconds. There's 12 seconds. It's taking a break. It's just hanging out at 6 meters. All right. Now I have this green portion of the line that I'm looking at. At 15 seconds there, this is 18, so at about 15 seconds, the object moves to 12 meters. 9, 10, 11, 12, 13, 14, 15, 16, 17. So about 17 seconds, the object's over here. That's 17 seconds. Okay, let's look at this blue portion of the line. What does the blue portion of the line mean? I'll assume this is 25 seconds here, this last point. At 25 seconds, where does the object end up? Well, if I go across, it looks like this is 6, this is 9 meters. So now my red ball is here at about 25 seconds. So what does that blue line represent? Well, it represents a negative slope, which means it's going down to the right, which means a negative velocity. So instead of my ball moving to the right, to the right, to the right, it actually ends up moving back to the left, and this is where it ends. So what did my ball do? Well, it started at 0 seconds, it moved to here, took a little break, then it moved to here really fast, and then it moved back to here really slowly and stopped there. So move to the right, to the right, to the right, move to the right really fast, took a little break, and then back to the left. Hopefully we're starting to get the idea with this stuff. The last thing actually doesn't show up in this section, but I just wanted to point it out. We're actually going to cover it in the next section we have. So velocity time graphs kind of just pop up all of a sudden. You've talked about distance or position time, distance time, position time graphs. And then all of a sudden I get to a graph that's velocity in time. And these are completely different. They mean completely different things. The slope means something completely different. A horizontal line means something completely different than a position time graph. If they were the same, we would just call them the same thing. They would all just be called position time graphs. But this is called a velocity time graph. Yeah, so Anna, you're 100% right. Everything we've done so far, talking about how objects are moving, we're just plotting it on a graph. And the reason we use graphs is because they can show a lot of information in a very small space. You can get a ton of information from a graph. We looked at the race of Bob and Ed. I wasn't there, I didn't see Bob and Ed race, but looking at the graph, I can see that they tied. They both ran 100 meters in 10 seconds, or got to 100 meters in 10 seconds. One of them got a 20-meter head start, didn't run as fast, so they finished at the same spot at the same time. I can tell exactly where each runner was at each given time, even though I wasn't there. So there you go. Velocity time graphs are completely different. We'll actually end up talking about them, but I just wanted to show why it's so important that you read the axes and figure out what's going on in terms of these graphs. So if I looked at, just really quickly, and we'll take a little breather, if I look at 0 seconds, the object's moving at 0 meters per second. These are all velocities now instead of distances. If I looked at 5 seconds, I go across, this looks like it's about, I don't know, what's that, 30, maybe 29. We'll pretend it's 30. What does that mean? Well, the object at 10 seconds is moving at 30 meters per second. Or 5 seconds, I should say. At 10 seconds, the object's moving at 60 meters. Oh, we're at meters per minute. So weird. So here it's going at 0. Now it's going 30. Now it's going 60. So the object's speeding up. What's happening here? We talked about a horizontal line on a distance time graph. It meant the object wasn't moving. What about on a velocity time graph? At 10 seconds, the object's moving at 60 meters a minute. At 15 seconds, the object's moving at 60 meters per minute. This is 60 meters per minute as well. So a horizontal line on a velocity time graph doesn't mean the object's not moving. It means the object's traveling at a constant velocity. It's not changing its velocity. All right. Now the object's going 60, now it's going 40, now it's going 20, now it's going 0. Now it's going negative 20, now it's going negative 40. So what's happening here? Well, the object's slowing down. Now the object's going backwards. Still going backwards, but it's slowing down going backwards. There's some crazy things happening here, and we'll talk about them all in a second. The important thing here is that you don't confuse the graphs with one another. Just because you have a horizontal line on a position time graph means the object's not moving. On a velocity time graph, it means it's moving at a constant velocity. There are very different things happening on these graphs, and it's important that you know the differences between them. If you get really confused, just draw a little picture. And it is confusing. Once you get a lot of experience with them, it becomes very easy, but for now, you've never seen them before. And they look the same, the lines look the same, everything kind of looks the same, but they mean very different things. So maybe we'll take a 10-minute break. It's 10:20. We'll take a 10-minute break, and at 10:30 we'll come back. We'll talk about section 9.1 a little bit. I have a feeling you guys have some questions about the learning guide, so maybe in 10 minutes we'll come back, have a quick look at the learning guide, and then I want to jump into 9.1 because I want to finish this material off, finish the course off this week. So we need to do that. Just keep rolling, and then I'll leave you guys with some work, and we'll go from there. So I'll see you guys back in 10 minutes. Get up, move around, grab a little drink, maybe some coffee, wake yourself up, a little snack, and we'll see you back in 10 minutes. Thanks. Hi guys, welcome back. If you could give me a green check mark, just so I know I'm not talking to myself. I'll go over a few questions from the learning guide, and then we will jump into section 9.1, just to kind of keep moving. I know, Taylor, before you asked about an actual slope calculation, and I said, yeah, I'll get to it. Or maybe it was somebody else. I will get to it, I promise. I haven't forgotten about that. So, just looking at the learning guide, what page are we on here? So page 6 says graphing motion, and then we're going to look at a bunch of the different types of questions involving graphing. Now, you can be asked about things like slopes or, like relative type questions, things of that nature. Sorry, doing two things at once. But the important thing is you just kind of understand what the slopes are. A positive slope, moving forward. Zero slope or horizontal line, not moving. And then a negative slope's moving backwards. The questions here from the learning guide are all talking about position time graphs or distance time graphs until you get to the question number 5. No. Yeah, they're all position time graphs. So I didn't mean to confuse you by showing you a velocity time graph. I just wanted to show you why it was so important that we know what the difference is, just so you don't kind of forget about it. So number 1 and 2 I think will be okay. This one's kind of a relative type thing. It's kind of like our race that we looked at before. I think you should be all right there. How did each runner take 10 meters? What's distance? Determine the speed of each runner. Show all the work. Let's look at number 4. It's actually asking us to find the speed of each runner. And we need to kind of find the slope here. So for question number 1, they only want us to explain it in relation to d versus t graphs. Yes, that's correct. Pretend like you haven't seen velocity time graphs yet. Again, I just wanted to show you the difference between the velocity time and position time graphs or distance time graphs. Let's look at this. I'm going to make this a little bit bigger just so we can see it a little bit more clearly. All right, it's asking us to find the speed of each of the runners. And remember, the speed is the slope of a position time graph. And in this case, we have jogger A and jogger B. And I will do one of them, and then I'll leave one of the others for you guys to do. Maybe I'll do jogger A. Here we go. So, jogger. So jogger A, speed, which just really means the slope of the line. Now, slope is just rise over run, and if you can remember that from math, then you'll be okay. If you want to think about it in terms of physics, or what we've been doing, you'd have something like this. Average velocity is the change in position. I guess that's not the letter I was hoping for. Change in position over a change in time. Which is just the same thing as delta y over delta x. In this case, although it doesn't say it, our x-axis here is time in seconds, and our vertical axis is position forward in meters, so that makes sense. But they're the same thing. Change in x over change in y, or sorry, change in y over change in x, change in d over change in t. Same thing. You can think of it either way. All right, so this means we're going to take the, again, I don't mean to confuse you, but a change in anything, I could have a change in x is going to be x2 minus x1. I could have a change in d, which is going to be d2 or d final minus d initial. A change in t is t final minus t initial. And if I was doing x's and y's, this would be y2 minus y1 over x2 minus x1. Now instead of 1's, I have i's, and instead of 2's, I have finals. So you can see how it's the exact same process as you guys went through with slopes, except I've just changed the letters. Now I need to go to my graph and find 2 points. Doesn't matter what 2 points are, as long as they're on jogger A's line, I should be okay. Kind of hard to see, but I'm going to pick this point here at the origin, or 0, 0, because I love doing calculations with zeros in them. Subtracting 0, adding 0, very easy math. So if you can ever pick a point that goes through the 0, 0, then do that. It'll make your life a lot easier in terms of calculations. And then I'll do this one up here. Those look like 2 good points. They're both on the line. Will there be questions like this where we have to convert our units? It's possible. I'm not going to rule it out. It would be kind of evil, but I wouldn't put it past the creators of our course or the creators of the provincial exam. So yeah, it's really important to kind of look at your units when you're going through this. It might ask for something different than the graph. I don't know. The fact that you're asking the question means that you know enough to watch your units to kind of be aware of it. So I think you'll be okay. I know you'll be okay. Just need to be careful. All right, so I have 2 points. This point down here is 0, 0, and I'm going to call this my initial point. So these are my i's. And then up here, I have 5, comma, so that's 20. And this is my final point. Now, this is literally exactly the same as the math questions we would have done in order to calculate the slope. So my final distance is going to be 20, or my y term, minus 0 over 5 minus 0. So I'm going to have 20 divided by 5, which is going to be 4. Now, my position is in meters, and my time was in seconds, I'll assume. So this is jogger A, 4 meters per second, and all I have here is forward for a direction. So there's not much I can do. I don't know if it's up, down, front, back, whatever it is. 4 meters per second forward. Now you're thinking to yourself, Mr. Borden, that was sure a lot of work just to find the slope. Couldn't I have just looked at the graph and said, he started 0, he went here, this was 20, a rise of 20, a run of 5, 20 divided by 5 is just going to give me 4. Yeah, for sure you could have done that, which would have been really easy. The problem with that is if the person didn't start at the 0, 0, finding the slope by just looking at the last point won't work. So if I had a line, for instance, that started here, that went to there, if I said, okay, this is 16 over 2, okay, 16 over 2, the slope of that is 8. Well, that's not true. What I would be doing is I would be going 16 minus 10, and then 2 minus 0. So 16 minus 10 over 2 minus 0 is going to give me 6 over 2, which is going to give me 3. So I can't just take the last point. I can't just take the end point. The only way I can just take the end point is if the object or the whatever I'm talking about person also goes through the origin. So just be careful on that. For question 2, how would we describe how we know? Are you talking about this guy? The slope of a distance versus time graph represents Speed. All right, so the slope of a distance time graph is speed. Describe 3 ways you know this to be true. I can think of one way. I could calculate the slope, and my units will be in distance versus time, which is a speed. Number 2, you could give an example, yeah, for sure. I would know how far I went in a given time. And I'm not sure what the last one. Average velocity is change in position over change in time. I would go with maybe those 3. You could give some examples, I suppose. So you could look at the units. You know how far you went in a given time. And then you could use the formula average velocity, which is the same thing as the slope, but it's perhaps a little bit different. Kind of a strange question. Obviously, they're looking for something really specific, probably out of the notes, but I don't know what they're hoping for there. So, I also have one thing to ask about a part of the final question. Okay, let's keep going through here. For number 4, you're going to find the slope of jogger B next and include that. So I did A for you. You can do jogger B. The motion of a race cart on a linear track shown below. When's the cart starting line, standing still, direction. What is the fastest speed? So when it says fastest speed, that is the steepest slope. So look for the steepest line. When does it happen? Average velocity of the cart between 0 and 20. So that's the slope again. Remember, slope is velocity. What is the average velocity of the cart of the entire trip? Have a go at F and see how you end up. I will go through that with you next day. I have a feeling a few of you will have questions on that one. So do your best there for F. Oh, that was the one that you wanted, Abby. All right, Ava. All these A names starting to get to me. Finding the average velocity, maybe I'll just give you a few hints. I guess there's a couple ways to do it. I would probably find the velocity in each time interval. Yes and no, Ava. Think about it this way. If you were driving to Vancouver and you were driving, through West Kelowna, that's a real slow go. So maybe you drove like 20 kilometers per hour for 10 minutes, and then the rest of the trip you traveled at 120 kilometers per hour. If I added those up and averaged them, I would get 140 divided by 2, so I get an average velocity of 70 kilometers per hour, but I only traveled that 20 kilometers per hour for a very short period of time, and then I traveled 120 kilometers per hour for a very long period of time. So you need to take into consideration how long you're traveling at each of the speeds. So just be careful on that. If you're traveling really slow for just a really short period of time, that shouldn't affect your entire average velocity because you only traveled slowly for a very small period of time. So given that, see what you can do. I will go over it for sure next day, Ava, so I don't want to ruin it for everyone else. I want everyone to have a go at it, see how you end up. There's more than one way to do it, so different people can do it different ways, and there's no way that's more correct than the other. I don't want to ruin it for anyone. Should you give direction and they're different? It may not be a good idea for the final question, but should you give a direction associated with positive and negative? So remember that the positive and negative is giving a direction. If I have a positive velocity, that's the direction. If I give you a negative velocity, well, that's a direction as well. Positive is going one way. Negative means the opposite of the positive. So when you guys say, should I indicate a direction, you don't have to get caught up in the north, south, east, west, forward, up, down, left, right sort of idea. Positive and negative are indicating directions. They're relative to one another, they're relative directions, but they are indicating a direction. So if the question doesn't have an east in it or a west in it, then your answer shouldn't either. If your question says they're moving forward and your answer is positive, it's moving forward. If your answer is negative, it's moving backwards. If you have a question where it says an object's moving up and you end up with a positive answer, okay, that object's moving up. If it's a negative answer, it means it's moving down. If it doesn't give you an up, a down, a forward, a backward, a left, or a right, your answer won't have one. And that is just a kind of a limitation of the question. So you don't have to force a direction, I guess. If they give you something, your answer should include it. If they don't worry about it. Because it's positive, that's indicating its direction. So positive is a direction. I don't know what the direction is, but positive means it's going the same way as, whatever you said in the question. So you don't have to write the word positive. If your answer is positive, then that's all you're expected to do. You don't have to write positive in brackets. If your answer is positive, go with that. If your answer is negative, put that in. That's all you can do. Unless they give you a direction on a graph or in the question, you can't indicate it. So you can only work with the information you're given. You can't make something up out of nothing. And yeah, I'll just leave it at that. If they don't give you a direction, you don't have to include a direction in your answer. If numbers in the question are positive and your answer is positive, then you know it's the same direction as whatever you're starting with. Yeah, so again, when you're saying direction, I wouldn't say forward or backward. I would just say positive and negative. Positive is a direction, negative is another direction. If I'm calculating the average velocity, let's not kid ourselves, we're looking at this. This portion of the graph here has a positive slope. This portion of the graph here has a negative slope. So I don't know what this slope is, I'll just make it up. I'll say it's 10, and then I'll say this is negative 10. Well, I haven't said that this is 10 to the east, and this negative 10 means 10 to the west, but I know the directions are opposite one another because this slope is positive and this slope is negative. So the positive and negative are indicating a direction for me. And then again here I have a positive slope. So positive and negative is a direction upon itself. Doesn't necessarily need to be east-west, forward, backwards. But the slope is positive, the slope is 0, the slope is negative. The actual numbers that are positive and negative are very important. If it's going down to the right and your slope is 12, it needs to be negative 12. It can't just be 12. And it's exact same as math. If you had a negative slope, it is a negative. And if you had a positive slope, it's positive. It's just that straightforward. Again, if you had a direction, you could include it. But even in our calculations, we're not going to write in north and south or east and west. It just confuses things. We use positive and negative to indicate that they're opposite directions to one another. Hopefully that's all right. I'll go through the answers to these next day if you guys end up with questions. I know you'll have a question about F for sure. So try it, but I have a feeling most of you will want to see it done anyways. Yeah, definitely on a provincial exam, you will not be expected to, well, you could be expected to draw a graph and find the slope from it if you're given some information, but it's all multiple choice, so you're never going to be marked on your graph. It's just the answer you're going to get from your graph. So, yeah, you'll never be expected to draw a graph to submit for an answer. You have multiple choice, so they could give you 4 graphs and you have to pick one, but never are your graphs going to be actually marked. All right, let's look at acceleration, chapter 9. So that ends chapter 8. I know we kind of started it and then took a break and then we came back to it, but it's not a long unit. There's not a lot of information there, a bit of calculation type stuff. Chapter 9, it looks exactly the same as chapter 8. And I'm just going to go through it like it was the same thing. Really, 8 and 9 should be together in one big test, but you get 2 little tests along the way. Okay, we've already talked about uniform motion today. Remember the pool ball that was rolling along the table with the flashes showing how far it traveled? And this is the same example here. Object traveling with uniform motion means that traveling the same distance in the same amount of time. So from 0 meters to 4 meters took 2 seconds. So that was a distance of 4 meters taking 2 seconds. The next 4 meters took 2 seconds. The next 4 meters took 2 seconds. So that is uniform motion. Now, before I asked you, what would non-uniform motion look like? And this is what it looks like. This car is going to the left. So from 0 to 2 meters, it took 2 seconds. If it were uniform motion, it should travel to 4 meters at 2 seconds, but now it's going from 2 to 8 meters in 2 seconds. So the first 2 seconds, or the first 2 meters took 2 seconds. Then 2 seconds later, now you're all the way up to 8 meters. So you've traveled 6 meters in the same amount of time. And then you travel another 2 meters in 2 seconds, and then you travel another 6 meters in 2 seconds. So you can see how the non-uniform motion looks. The object is changing its velocity. It's traveling a different distance for the same time interval. Each one of these time intervals is 2 seconds. But here it's only moving 2 meters, and then here it moved 4 meters, and here it's moved 6 meters, each of those time intervals. So that is non-uniform motion. Now we've talked about